Hello friends, welcome you in my YouTube channel. I am Dr. Mohammad Sirajul Faisi, Assistant Professor, Department of Chemistry, LS College, Muzaffarpur. Friend, today in this video I am going to explain about NMR, Nuclear Magnetic Resonance. So let us start with the chemical shift. You know the chemical shift is the exact field strength in ppm of nuclei comes into resonance relative to reference standard TMS. I already talked much more about the TMS structure and their character of 16 hydrogens, 12 hydrogens, 6, 9 and 12 hydrogens. So I talk about the methyl acetate spectra. Now I am going to talk about vertical scale, and that is the vertical scale. Intensity of the signal. Horizontal scale, chemical shift. You have the x-axis and you have the y-axis. X-axis in NMR spectra, chemical shift, it is denoted by delta, and y-axis intensity, and this is the ppm of unit. So vertical scale, intensity of the signal, intensity of the signal, and horizontal scale, chemical shift, delta, depends upon field strength. That is very important. Delta depends upon the field strength of external magnetic field. Magnetic field means external magnetic field is here. You see, randomly oriented nuclei, after applying external magnetic field, some aligned, some opposed, and they create energy. So external magnetic field for proton NMR, delta is usually from 1 to 10 ppm, usually, because I am not talking about the metal hydride. So delta is equal to nu minus nu TMS nu naught. Chemical shift in hertz and operating frequency in megahertz. This, whenever you will go in an NMR machine, you will find there is written 400 megahertz. So what is the operating frequency in megahertz and what is the chemical shift? Chemical shift in hertz and it is in megahertz, and this is your standard tetramethylsilane. So 4100 Gauss, 60 megahertz for proton NMR, 60 million hertz, ppm 60 hertz, 50 megahertz for carbon 13, and 140 not Gauss, 600 megahertz for proton, 150 megahertz for carbon 30, ppm 600 hertz. So just remember the hertz, and this is the Gauss. So equivalence, chemically and magnetically equivalent nuclei resonance at the same energy and give a signal or pattern. Look at this environment. This compound contains 12 proton. Look at here, CH3, 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 CH3. So all proton are in same environments. Your y-axis is intensity and your x-axis is chemical shift. We called it delta, and this is your standard TMS, tetramethylsilane, and there is no peak except this rate. So what it is indicating? it indicates there are proton present in this molecule, all are in the same type and same environment. So equivalence means chemically and magnetically. What? Chemically and magnetically equivalent nuclei resonate at the same energy and give a single signal or pattern. Single signal or pattern. This is single signal or pattern. So, and this is a single and singlet. So this 3 and this 3 6 and this 3 9 and this 3 12 proton are in same environment, because this carbon and this carbon and this carbon and this carbon in the same environment. So all 12 proton are same environment. That's why you are getting a single peak in your NMR spectra. What is you are expecting when you synthesize this type of compound? You expect single peak in your NMR spectra without splitting, because this 3 hydrogen is not near to any hydrogen. So equivalence, chemically and magnetically equivalence. Friends, now look at here. What happened? You just change one proton, one hydrogen with methyl group, and NMR spectra completely change. You have here one, but here you can look at how many. 1, 2, 3, 4. Because now little bit you're changing, it create different environment. Now we have 4 types of proton: red one, green one, and blue one, and black one. This is your x-axis and this is your y-axis. Y-axis indicate intensity and x-axis indicate chemical